Resistance grounding is a technique used in electrical systems to limit the amount of ground fault current that can flow during a fault condition. This is achieved by inserting a resistor between the neutral point of the system and ground. This resistor limits the current that can flow during a ground fault. In a solidly grounded system, the neutral is directly connected to ground, allowing for very high fault currents. A 4-line diagram can help illustrate this concept. Imagine a power source such as a transformer providing power to a load, which is the equipment being supplied. There are supply lines carrying power to the load and a neutral line connected to ground through a resistance, labeled Rg. During a fault, for example, between one of the supply lines and ground, current flows through the fault and the resistance Rg to ground. Because of the resistance, the fault current is limited compared to a solidly grounded system. The effect of this limited current on an electrician touching the faulted equipment is significant. The electrician will be exposed to the limited fault current. This limited current reduces the severity of an electric shock, potentially preventing serious injury or death. In contrast, a solidly grounded system allows for much higher fault currents, which result in a more severe electric shock hazard. Resistance grounding provides additional protection for electricians working on faulted equipment. Now, let's consider the advantages and disadvantages of resistance grounding compared to solidly grounded systems. Firstly, resistance grounding limits the ground fault current, reducing the risk of equipment damage and arc flash hazards. Secondly, it allows for continued operation of equipment during a ground fault, which is critical in certain applications. Thirdly, it simplifies ground fault location, making it easier to identify and repair faults. However, resistance grounding also has some disadvantages. 1. It requires the use of a ground fault monitoring system to detect and respond to ground faults. 2. The system voltage may rise during a ground fault, potentially stressing insulation. 3. It may not be suitable for all types of electrical systems. Now, considering safety precautions, it is essential to understand that resistance grounding is not a substitute for proper safety procedures. The electrician should always wear appropriate personal protective equipment or PPE, such as insulated gloves and safety glasses, and follow safe work practices. It is important to energize equipment before working on it whenever possible. Also, high impedance arc faults in solidly grounded systems can pose a hazard if circuit breakers fail to trip. Resistance grounding systems are often used in critical facilities to minimize the risk of catastrophic failures. When assessing the dangers to a worker, it is important to consider the potential for high impedance arc faults in solidly grounded systems, which may not trip upstream circuit breakers. Resistance grounded systems, while offering advantages, still require careful consideration of safety protocols and the use of PPE. The key takeaway is that resistance grounding limits fault current, reducing the severity of electric shock and potential for equipment damage, but it does not eliminate the need for safe work practices and appropriate PPE. The limited ground fault current in a resistance grounded system affects an electrician by reducing the severity of electric shock if they come into contact with faulted equipment. The resistance in the grounding path limits the current flow, minimizing the potential for serious injury compared to a solidly grounded system where fault currents can be much higher. Consider a scenario where a fault occurs in a piece of equipment connected to a resistance grounded system. The fault current will flow through the grounding resistor, limiting its magnitude. If an electrician accidentally touches the faulted equipment, the current passing through their body will be significantly lower than what they would experience in a solidly grounded system. This reduced current minimizes the risk of severe burns, cardiac arrest, and other life-threatening injuries. The 4-line diagram visually represents the flow of current during a fault in a resistance grounded system. It typically includes the power source, supply lines, the grounding resistor, the load, and the fault location. The diagram illustrates how the grounding resistor limits the fault current and diverts it back to the source, minimizing the potential hazard to personnel and equipment. High impedance faults, such as arcing faults, can occur in both solidly grounded and resistance grounded systems. However, resistance grounding can help mitigate the impact of these faults by limiting the available fault current and reducing the likelihood of sustained arcing. While resistance grounding offers significant safety benefits, it is crucial to implement a comprehensive ground fault protection scheme. This includes ground fault relays, current transformers, and other devices that can detect and respond to ground faults quickly and effectively. Ground fault relays are designed to trip the circuit breaker when a ground fault is detected, isolating the faulted equipment and preventing further damage or injury. Current transformers are used to measure the ground fault current and provide a signal to the ground fault relay. These devices work together to provide a reliable and effective ground fault protection system. Additionally, regular testing and maintenance of the grounding system are essential to ensure its continued effectiveness. This includes inspecting the grounding connections, verifying the resistance of the grounding resistor, and testing the ground fault relays. Proper maintenance helps to identify and address any potential issues before they can lead to a dangerous situation. In summary, resistance grounding is an effective technique for limiting ground fault current and improving electrical safety. By reducing the severity of electric shock and minimizing the risk of equipment damage, resistance grounding helps to protect personnel and maintain the reliability of critical electrical systems. However, it is important to remember that resistance grounding is not a substitute for proper safety precautions and a comprehensive ground fault protection scheme. Electricians should always wear appropriate PPE, follow safe work practices, and be aware of the potential hazards associated with working on electrical equipment. The effectiveness of resistance grounding depends on several factors, including the value of the grounding resistor, the system voltage, and the type of equipment being protected. The grounding resistor should be sized appropriately to limit the fault current to a safe level while still allowing for a reliable detection of ground faults. The system voltage also affects the magnitude of the fault current, with higher voltages resulting in higher fault currents. The type of equipment being protected may also influence the choice of grounding method, with some equipment being more sensitive to ground faults than others. There are different types of resistance grounding, including low resistance grounding and high resistance grounding. Low resistance grounding typically limits the fault current to several hundred amps, while high resistance grounding limits the fault current to a few amps. Low resistance grounding is often used in high voltage systems where it is important to quickly clear ground faults and minimize equipment damage. High resistance grounding is often used in low voltage systems where it is desirable to maintain service continuity during a ground fault. The choice between low resistance grounding and high resistance grounding depends on the specific application and the desired level of protection. When designing a resistance grounded system, it is important to consider the coordination of the ground fault protection devices. The ground fault relays should be coordinated to trip in a specific sequence, isolating the faulted equipment and minimizing the impact on the rest of the system. Coordination studies are typically performed to determine the appropriate settings for the ground fault relays. These studies take into account the characteristics of the electrical system, the grounding impedance, and the desired level of protection. Proper coordination of the ground fault protection devices is essential to ensure that the system operates safely and reliably. In addition to the technical aspects of resistance grounding, it is also important to consider the human factors. Electricians and other personnel should be properly trained on the principles of resistance grounding and the potential hazards associated with working on electrical equipment. Training should include instruction on the proper use of PPE, safe work practices, and the operation of ground fault protection devices. Regular refresher training should also be provided to ensure that personnel remain knowledgeable and proficient in these areas. By addressing both the technical and human factors, it is possible to create a safer and more reliable electrical system. The benefits of resistance grounding extend beyond the protection of personnel and equipment. Resistance grounding can also improve the reliability of the electrical system by reducing the likelihood of nuisance tripping. Nuisance tripping occurs when a circuit breaker trips unnecessarily, interrupting power to critical equipment. Resistance grounding can help to prevent nuisance tripping by limiting the magnitude of transient overvoltages that can occur during switching operations or other disturbances. By reducing the likelihood of nuisance tripping, resistance grounding can improve the uptime and productivity of industrial facilities and other critical operations. Furthermore, resistance grounding can also reduce the risk of fire and explosion. Ground faults can generate significant heat, which can ignite flammable materials and cause a fire or explosion. By limiting the magnitude of the fault current, resistance grounding can reduce the risk of these events. This is particularly important in hazardous locations where flammable materials are present. In these locations, resistance grounding is often required by code to minimize the risk of fire and explosion. The installation of a resistance-grounded system typically involves several steps, including selecting the appropriate grounding resistor, installing the grounding conductor, connecting the grounding resistor to the neutral point of the system, and testing the grounding system. The grounding resistor should be selected based on the system voltage, the desired fault current limit, and the type of equipment being protected. The grounding conductor should be sized appropriately to carry the fault current and should be installed in accordance with applicable codes and standards. The grounding resistor should be connected to the neutral point of the system using a low impedance connection. After the grounding system is installed, it should be tested to verify its effectiveness. This testing typically involves measuring the resistance of the grounding resistor and verifying the operation of the ground fault protection devices. The testing should be performed by qualified personnel using appropriate test equipment. The maintenance of a resistance-grounded system is essential to ensure its continued effectiveness. Regular maintenance should include inspecting the grounding connections, verifying the resistance of the grounding resistor, testing the ground fault relays, and inspecting the grounding conductors. Any damaged or corroded component should be replaced promptly. The maintenance schedule should be based on the manufacturer's recommendations and the operating environment. Proper maintenance can help to identify and address any potential issues before they can lead to a dangerous situation. In addition to the technical and human factors, it is also important to consider the regulatory requirements related to resistance grounding. Many codes and standards, such as the National Electrical Code or NEC, provide specific requirements for resistance grounding systems. These requirements address issues such as the size of the grounding conductor, the location of the grounding resistor, and the testing and maintenance of the grounding system. It is important to be familiar with the applicable codes and standards and to ensure that the resistance-grounded system complies with these requirements. Compliance with regulatory requirements is essential to ensure the safety and reliability of the electrical system. In conclusion, resistance grounding is a valuable technique for improving electrical safety and reliability. By limiting the magnitude of ground fault current, resistance grounding can protect personnel from electric shock, reduce the risk of equipment damage, prevent nuisance tripping, and minimize the risk of fire and explosion. However, it is important to remember that resistance grounding is not a substitute for proper safety precautions and a comprehensive ground fault protection scheme. The electricians and other personnel should always wear appropriate PPE, follow safe work practices, and be aware of the potential hazards associated with working on electrical equipment. By addressing both the technical and human factors and by complying with regulatory requirements, it is possible to create a safer and more reliable electrical system.